Let's continue to read the book Until the End of Time by Brian Greene. The first chapter and this section's title is Entropy, a First Pass. Entropy is among the most confusing concepts in fundamental physics, a fact that has not diminished, and the cultural appetite for freely invoking it to describe everyday situations that have evolved from order to chaos, or more simply, from good to bad. As colloquial usage goes, this is fine. At times, I have invoked entropy that way too. But as the scientific conception of entropy will guide our journey and also lies at the heart of Russell's dark vision of the future, let's tease out its more precise meaning. Start with an analogy. Imagine you vigorously shake a bag containing 100 pennies and then dump them out on your dining room table. If you found that all 100 pennies were heads, you would surely be surprised. But why? Seems obvious, but it's worth thinking through. The absence of an even single tail means each of the 100 coins, randomly flipping, bumping, and jostling, must hit the table and land heads up, all of them. That's tough. Getting that unique outcome is a tall order. By comparison, if we consider even a slightly different outcome, say in which we have a single tail and the other 99 pennies are still all heads, there are 100 different ways this can happen. The long tail could be the first coin, or it could be the second coin, or the third, and so on, up to the 100th coins. Getting 99 heads is thus 100 times easier, 100 times more likely than getting all heads. Let's keep going. A little figuring reveals that there are 4,950 different ways we can get two tails, first and second coins tails, first and third tails, second and third tails, first and fourth tails, and so forth. A little more figuring, and we find that there are 161,700 different ways to have three of coins come up tails, almost 4 million ways to have found to have 4 tails, and about 75 million ways to have 5 tails. The details of the numbers hardly matter. It's the overall trend I'm driving at. Each additional tail allows for a far larger collection of the outcomes that fit the bill, phenomenally larger. The numbers peak at 50 tails and 50 heads, for which there are about 100 billion possible combinations. Getting 50 heads and 50 tails is therefore about 100 billion times more likely than getting all heads. That's why getting all heads would be shocking. My explanation relies on the fact that most of us intuitively analyze the collection of pennies, much as Maxwell and Boltzmann advocated, analyzing a container of steam. Just as the scientists turned a cold shoulder to analyzing the steam molecule by molecule, we typically don't evaluate a random collection of pennies coin by coin. We hardly care or notice if the 29th penny is heads or the 71st is tails. Instead, we look at the collection as a whole. And the feature that catches our attention is the number of heads compared to the number of tails. There are more heads than tails or more tails than heads? twice as many, 3 times as many, roughly equal amounts, we can detect significant changes in the ratio of heads to tails, but the random arrangements that preserve the ratio, like flipping the 23rd, 46th, and 92nd coins from tails to heads, while also flipping the 17th, 52nd, and 81st coins from heads to tails, are virtually indistinguishable. Consequently, I dived after the possible outcomes into groups, each containing those configurations of coins and that pretty much look the same, and I enumerated the membership of each group. I counted the number of outcomes with no tails, the number of outcomes with 1 tail, the number of outcomes with 2 tails, and so on, up to the number of outcomes with 50 tails. The key realization is that these groups do not have an equal membership, not even close. That made it obvious why you would be shocked for a random shake of the pennies to yield no tails. Slightly less shocked for the random shake to yield 1 tail. A touch less shocked still to find 2 tails. But you would yarn if the shake yields a configuration that is half heads and half tails. The greater the membership in a given group, the more likely it is that the random outcome will belong to that group. Group size matters. If this material is new to you, you may not realize that we have now illustrated the essential concept of entropy. The entropy of a given configuration of the pennies is the size of its group. The number of fellow configurations that pretty much look like the given configuration. If there are many such look alike, the given configuration has high entropy. If there are a few such look-alikes, the given configuration has low entropy. All else being equal, a random shake is more likely to belong to a group with a higher entropy, since such groups have more members. This formulation also connects with the colloquial uses of entropy I referenced at the offside of this section. Intuitively, messy configurations, think of a chaotic desktop piled high with scattered documents, pens, and paper clips, have a high entropy because a great many rearrangements of the constituents all pretty much look the same. Randomly rearrange a messy configuration and it still looks messy. Orderly configurations, think of a pristine desktop with all documents, pens, and paper clips neatly placed in their designated positions, have a low entropy because very few rearrangements of the constituents look the same. As with the pennies, high entropy beckons because messy arrangements far outnumber orderly ones. Next section, entropy, the real deal. The pennies are particularly useful because they illustrate the approach scientists developed for dealing with the voluminous collection of particles constituting physical systems, whether water molecules fleeting to and fro in a hot steam engine or air molecules drifting across the room in which you are now breathing. As with the pennies, we ignore the details of individual particles. Whether any one particular molecule of water or air happens to be here or there is of little consequence, and instead group together those configurations of the particles that pretty much look the same. For the pennies, The criterion for look-alikes invoke the ratio of heads and tails because typically we are indifferent to the disposition of any particular coin and generally take note only of the configurations of overall appearance. But what does pretty much look the same mean for a large collection of gas molecules? Think about the air now filling your room. If you're like me and the rest of us, you couldn't care less whether this molecule of oxygen is floating by the window or that molecule of nitrogen is bouncing off the floor. You care only that each time you inhale, there is an adequate volume of air to meet your needs. Well, there are a couple of other features you likely care about too. If the air's temperature was so hot that you scorched your lungs, you would be unhappy. Or if the air's pressure was so high and you hadn't equalized it with the air already in your eustachian tubes that you burst your eardrums, you would be unhappy too. Your concern then is with the air's volume, the air's temperature, and the air's pressure. Indeed, these are the very macroscopic qualities that the physicists from Maxwell and Boltzmann on through today care about too. Accordingly, for a large collection of molecules in a container, we say that different configurations pretty much look the same. If they fill up the same volume, have the same temperature, and exert the same pressure, much as with the pennies we grouped together, all look alike configurations of the molecules and say that each member of the group gives rise to the same macrostate. The entropy of the macrostate is the number of such look-alikes. Assuming you are not just now turning on a space heater, affecting temperature, or putting up an impermeable room divider, affecting volumes, and pumping in additional oxygen, affecting pressure, the ever-evolving configuration of air molecules floating to and fro in the room you are now inhabiting all belong to the same group. They all pretty much look the same, as they all yield the very same macroscopic features you are currently experiencing. The organization of particles into groups of look-alike provides an extraordinarily powerful schema. Just as randomly tossed pennies are more likely to belong to a group with a greater membership with higher entropy, so too for randomly bouncing particles. The realization is as straightforward as its implications are far-reaching. Whether the bouncing particles are in a steam engine, in your room, or anywhere else, by understanding the typical features of the most commonplace of configurations, those that belong to the groupings with the greatest membership, we can make predictions about the system's macroscopic qualities, the very qualities we care about. These are statistical predictions, to be sure, but ones with a fantastically high probability of being accurate. And the kicker is that we achieve all this while avoiding the insurmountable complexity of analyzing the trajectories of an absurdly large number of particles. To carry out the program, we therefore need to sharpen our ability to identify commonplace, that is high entropy versus rare, low entropy particle configurations. That is, given the state of a physical system, We needed to determine whether there are many or few rearrangements of the constituents that would leave the system looking pretty much the same. As a case study, let's visit your steam-filled bathroom just after you have taken a long hot shower. To determine the steam's entropy, we need to count the number of configurations of the molecules, their possible positions, and their possible speeds, that all have the same macroscopic properties, that is, have the same volume, same temperature, and the same pressure. Carrying out the current mathematically for a collection of H2O molecules is much challenging than the analogous account for a collection of pennies, but is something most physics majors learn to do by their sophomore year. More straightforward and more enlightening too is working out how volume, temperature, and pressure qualitatively affect entropy. Volume first. Imagine that the fleeting H2O particles are tightly clustered in one tiny corner of your bathroom, creating a dense knot of steam. In this configuration, the possible rearrangements of the positions of the molecules will be sharply curtailed. As you move the H2O molecules around, you have to keep them within that knot, or else the modified configurations will look different. By comparison, when the steam is evenly spread throughout your bathroom, the game of molecular musical chairs is far less constrained. You can exchange the positions of molecules near the vanity with those floating by the light fixture, those near the shower curtain with those hovering by the window, and yet overall the steam will look the same. Note too that the bigger your bathroom, the greater the number of locations you have for sprinkling around the molecules, which also increase the number of rearrangements available. The conclusion then is that smaller and tightly clustered configurations of molecules have a lower entropy, while larger and evenly spread configurations have a higher entropy. Temperature next. At the level of molecules, what do we mean by temperature? The answer is well known. Temperature is the average speed of a collection of molecules. Something is cold when the average speed of its molecules is low, and it is hot when the average speed is high. So determining how temperature affects entropy is tantamount to determining how the average molecular speed affects entropy. And much as we found with molecular positions, a qualitative assessment is close at hand. If the temperature of the steam is low, the allowed rearrangements of the molecular speeds will be comparatively few in number. To keep the temperature fixed, and thus ensure that the configurations all pretty much look the same, you have to offset any increase in the speeds of some molecules by a suitable decrease in the speeds of others. But the burden of having low temperature, low average molecular speed is that you don't have a lot of room to decrease the speeds before hitting rock bottom zero. The available range of possible molecular speeds is thus narrow, and so your freedom to rearrange the speeds is limited. By comparison, if the temperature is high, your game of musical chairs once again revs up. With a higher average, the range of molecular speeds, some larger than the average and some smaller, is much wider. providing greater latitude for mixing up the speeds while preserving the average. More arrangements of the molecule speeds that all pretty much look the same means that the higher temperature generally entails higher entropy. Finally, pressure. The pressure of the steam on your skin or on the bathroom walls is due to the impact of streaming H2O molecules that slam into the surface. Each molecule impact exerts a tiny push, and so the greater the number of molecules, the higher the pressure. For a given temperature and volume, pressure is that determined by the total number of steam molecules in your bathroom, a quantity whose consequences for entropy can be worked out with the greatest of ease. Fewer H2O molecules in your bathroom, you look at the shorter shower, means fewer rearrangements are possible, and so entropy is lower. More H2O molecules, you took a longer shower, means more rearrangements are possible, and so entropy is higher. To summarize, having fewer molecules or having lower temperature or filling a smaller volume results in lower entropy. Having more molecules or having higher temperature or filling a larger volume results in higher entropy. From this brief survey, let me underscore one way of thinking about entropy. Lacking in precision but providing a useful rule of thumb, you should expect to encounter high entropy states, because such states can be realized by a great many different arrangements of the constituent particles. They are typical, pedestrian, easily configured, a dozen. By contrast, if you encounter a low entropy state, it should command your attention. Lower entropy means there are far fewer ways to the given microstate can be realized by its microscopic ingredients, and so much configurations are hard to come by. They are unusual. They are carefully arranged. They are rare. Step after a long hot shower and find the steam uniformly spread throughout your bathroom, high entropy and totally unsurprising. Step after a long hot shower and find the steam all clustered in a perfect little cube hovering in front of the mirror. Low entropy and extraordinarily unusual. So unusual, in fact, that were you to encounter such a configuration, you should be extremely skeptical of the explanation that you have simply come upon one of those unlikely things that on occasion happen. That could be the explanation, but I would bet my life it isn't. Just as you would suspect there is a reason beyond mere chance that 100 pennies in your dining room table are all heads, such as someone judiciously flipped over each coin that lands tails. You should seek explanation beyond mere chance for any low entropy configurations you encounter. This reasoning applies even to the seemingly mundane, like coming across an egg or an anthill or a mug. The orderly, crafted, low-entropy nature of these configurations calls out for explanation. That the random motion of precisely the right particles could just happen to coalesce into an egg or an anthill or a mug is conceivable, but far-fetched. Instead, we are motivated to find more convincing explanations. And of course, we don't have far to search. The egg and the anthill and the mug each arise from particular forms of life arrangement, the otherwise random configuration of particles, in an environment to yield orderly structure. How life is able to produce such exquisite order is a theme we will address in later chapters. For now, the lesson is simply that low entropy configurations should be viewed as a diagnostic, a clue that powerful organizing influences may be responsible for the order we have encountered. In the late 1800s, armed with the ideas, many of his own devising, Austrian physicist Ludwig Boltzmann believed he could address the question that launched this section of our discussion. What distinguishes the future from the past? His answer relied on the quality of entropy, particularly by the second law of thermodynamics. Let me stop here, and we'll continue for the next one later.